All right, so yesterday we talked about homogeneous equations. Now we're going to go ahead and wrap this unit up with exact equations. And we'll start by taking a look at the equation y dx plus x dy equal to 0. That's fine, just throw them on the table. Thank you, guys. And hopefully you notice two things. One, could I do this by separating variables? Yeah, right? Could we also treat this, not that anyone would want to, as a homogeneous equation? Okay? Now, let's also examine this expression. Oh, that's not where I meant to put the prime, sorry. If we have the product of x and y prime, okay, equal to 0, I claim that this is identical to this, okay? And hopefully you see that with the product rule. Of course, it is. I mean, you could do derivative with respect to x is y, derivative, let's see, so we have x dx, x times dy dx equal to 0. Okay, so derivative of x is y, dx is 1, and then derivative of y is just going to be x, then we get dy dx. Okay, and if you go ahead and multiply through by dx, there you have it. Okay, so the argument here is that this and this are equal. Okay, it's the same thing. And the nice thing about recognizing that this equation could also be written like this is that now if you were to integrate this, okay, when you take the integral of the derivative of the product of x and y, what do you suppose that would be? xy, good. And obviously here we get constants. So xy equals c would be the solution to this differential equation, which you could also obtain by separating variables, treating it as a homogeneous equation, doing a substitution which makes it separable, which no one would do, and then certainly if you recognize that this differential here is the derivative of the product of x and y, you can just take the derivative of this, or the integral of this derivative, and then you have your solution. Okay, so if you recognize it, so if you recognize the differential as a product, it's easy to solve. Okay. I guess before we do the next part, we should also revisit this. So recall that if z is equal to f of xy, and we set that equal to 0 or some constant, the differential dz would be equal to what? Sorry, Calc 3 again. You guys remember? Partial f, partial x, good. We're missing one thing. Before that. Dx. And then you're right. Partial f, partial y, dy. Okay. Now, if it's equal to a constant, then we're going to get 0, right? Well, and this is really saying the same thing, okay? So if we go back, let's see if I can squeeze it on the top there. If you go back to this equation, it really did come from this. Okay, if you take a look, right? Partial f, partial x for xy would be just x, okay? And then, or I'm sorry, it would be y dx. And then if we did partial f, partial y, for the product of x and y, that'd be x. Okay, and then we have our dy. So this differential equation came from a product. It also is going to help us to remember that if we define the product as a function of two variables of x and y, okay, that this is also equivalent to that. Okay? All right. Let's look at an example. Let's say I have x squared minus 5xy plus y cubed equal to c. So here's our function of x and y, and that's equal to c. Following this prescription here, where we look at our function of x and y and then write it out in this form, okay, we're going to get 0, and then partial f, partial x would be what here? Look at the function. Think Calc 3 for a moment. Right? What's partial x going to be? 2x minus 5y. Good. Plus, and now we do partial f, partial y, which would be negative 5x. Thank you. And there is a dy here. Okay, so here's the thing. Sorry, I keep wanting to stand up and go point at things, but I shouldn't do that because then they won't hear me. This is our starting point. Oops. So you're going to start with the differential equation that looks somewhat like this. 2x minus 5y dx plus negative 5x plus 3y squared dy. It's going to be hard to see that this is the product, right? That this is the function that you actually were taking the derivative of to get to this equation. Okay, so let's make a point of that. So it's hard to see that dy dx, if I wrote it in the dy dx form, it'd be negative of 2x minus 5y over negative 5x squared plus 3y squared. It's hard to see that this differential equation or this differential equation came from the expression or from the equation x squared minus 5xy plus y cubed prime. Okay, so we're trying to come up with a way to see if we can recognize whether it's an exact equation or not, because if we recognize that it's exact, there's going to be a method that we can utilize. But obviously it's kind of hard to just look at it and say, oh, well, this clearly came from the derivative of that. Okay, so that's the problem currently. Okay, so here's the definition, and we'll get to a trick in a moment. a differential expression let's call it m of xy dx plus n of xy dy is an exact differential of differential expression is an exact differential, if it is the total differential. So there's the little bit of Calc 3 coming back of some function f of xy. A differential equation of this form equal to 0 is called an exact equation. Okay. We don't need to do the next example. I think all you guys see what the problem is currently, right? We want to know when it's exact. Sometimes you can kind of eyeball it and say, oh, that's an exact expression. We can treat it as a product of this and that, and then we can integrate. Other times, like for this example here above, I mean, unless you're pretty crafty, it'd be pretty hard to see that this was the derivative of this function here. Okay, so that's currently where we're at. Now, going on to the theorem for this section, which we're not going to prove because some of you may already know where this is headed, but this is how we're going to know if it's exact. Okay, so we're going to let m of xy and n of xy be continuous and have continuous first partials. And let's say that this is in a region defined, let's call it R, defined by A, which is less than or equal to X, which is less than or equal to B, and let's say Y is between or equal to C and D. All right. So what we're talking about is the are the coefficients of dx and dy. Okay. We're going to say that m of xy dx plus n of xy dy is exact if and only if partial m partial y equals partial n partial x. Okay. Does this look familiar to you guys? What's that? I can't hear you. Yes, the conservative test for vector fields, right? Remember when we did that in 15.4-ish or 15.3? If we took, oh yeah, they can't see me doing this. If they took this expression here, put a little integral in front of it, line integral, right, closed path, this is now the vector field, or the integral of a conservative vector field. Does that look familiar? Okay. And then when we wanted to solve that, you guys remember how we found the vector, or how we integrated that? By finding the potential function? Some of you are saying yes, some of you are like, I know all the terminology, but I don't remember what we did. Okay. Here's what it looks like. Okay, so I'm glad some of you are recognizing that this is similar to what we've done, and I will go ahead and say that the solution is the analog of finding the potential function for a conservative vector field. Okay? And I think as we do this example here, it'll start coming back to you. Alright, so let's actually go ahead and get down to business and start solving these. So if we have 9x squared y dx plus, let's say, 3x cubed plus 1 dy equal to 0. Okay, at this point, what you try to do is see if you recognize what kind of equation it is. So obviously you can try to separate, and in this case, looks like you can separate. You can just divide this expression, so then it comes up over here as 9x squared over 3x cubed plus 1 dx. And then you can divide by y. So you could separate, but the integration might be a little nasty. Okay, so it's not homogeneous. What degree is this coefficient? This is degree 3, and then this one is, well, this part is degree 3, and that part's degree 0, so it's not homogeneous, right? So let's go ahead and treat it as an exact equation, but first we got to check to see if partial m partial y equals partial n partial x. So look at the coefficient for dx. What's the partial derivative with respect to y? 9x squared. And partial n partial x. So now look at the second coefficient. What's the derivative there? 9x squared. Okay, so this is exact. And the solution is going to look very familiar at this point. So we're looking for f of x, y. Well, we know that f of x, y, if we were to integrate partial f partial x dx, we'd get what the we'd get what the function f of x, y looks like, right? So partial f partial x, well, that's really this coefficient here in front of dx, right? So if we go ahead and integrate 9x squared y with respect to x, that becomes 3x cubed y plus, bless you, some constant, which could or could not be, maybe it is, maybe it's not, in terms of y. Okay. Do you guys remember what to do from here? So now you take the partial derivative of this with respect to y and you compare it with the coefficient for y. So since partial f partial y is equal to 3x cubed plus 1, okay, we're going to go ahead and take the partial derivative of what we say is the f of xy function, And in that case, we would get what? So differentiate this with respect to y, you get 3x cubed plus, if this were a function in terms of y, now it would be its derivative, right? Well, since we know what partial fy, or partial f partial y looks like, this means that g prime of y has to equal 1. So what do we do here? Integrate. So we get g of y is equal to y. Okay? And yes, we do have a little plus c here, but here's why it's not going to matter. The solution for these is always f of xy equal to the constant. Okay, so we're going to say 3x cubed plus y equal to c. Okay, so when you integrate, oh, am I missing something? 3x cubed y, I dropped it out, yes. Oh, and that's actually a common mistake. Here's how you make sure that you don't do what I just did, because that was not good. Here's f of xy, right? So when you start writing it down, okay, go back to f of xy, write out 3x cubed y, and then now replace g of y we know is y. Okay? Thank you.
G of y is 3x cubed y is equal to c 3x cubed y minus y.
Where are you getting the minus y from?
Well, you said that g of y equals y plus c. And isn't g of y 3x cubed y? Oh, no, I'm sorry.
That 3x cubed y, that's just part of f of xy. Or we can say that's partial f. Well, that's part of it. Not sure where you're getting the minus y from.
I saw the
Oh, you did? Okay. Alright, we good? Alright. Do we need another example like this, or now that we've kind of seen the procedure, we're good? Yes, we're good, or yes, we need an example? Junwan, what do you think? Move on?
Yeah.
Okay. All right, so the last part in this section is the definition or introduction to an integrating factor. Okay, and the notion or the idea behind this is that sometimes if you have an equation that is not exact, you might be able to turn it into an exact differential equation. Okay, so it is possible to turn an ordinary differential equation into an exact equation by multiplying by what we call an integrating factor. And we'll define that as mu of xy. Okay, so let's say we have m of xy dx plus n of xy dy equal to 0. And let's suppose that right now, let's suppose that it's not exact. then what we're saying is that if you were to multiply the entire equation by this mu of xy, I'll drop the of xy notation, we'd say that mu times m of xy dx plus mu times n of xy dy equals 0 is now exact. Okay. So here's an example to illustrate this point, and then we'll wrap things up. Say we have minus y squared dx plus x squared plus xy dy equal to 0. Okay, now later on we'll talk more about how to actually find them. Right now you will be told use the integrating factor mu equals whatever, and then that's how you're going to proceed. It is important to kind of go over this though, that we could go ahead and solve this now with what we know, right? Anybody see how? It's homogeneous. What degree? What substitution would you use? X equals Vy, okay? Good to go. So we know how to do it already, okay? But just to illustrate that we could do this as an exact equation, I will go ahead and tell you that mu, oh no, okay, thought it died on me. If you use mu equal to 1 over x squared y, that then this becomes an exact equation. Okay, so let's look. Let's go ahead and multiply by the integrating factor and see what happens. So we'd get minus y squared over x squared y. Actually, let's go ahead and simplify that so we don't have to write it down again. If I multiply by 1 over x squared y, this becomes minus y over x squared dx plus, and now this term would just be 1 over y plus, and now the second term would just be 1 over x. Okay? And if we check, let's do partial m partial y. What's the derivative there? Minus 1 over x squared. And if you look at the second coefficient with respect to x, you get the same thing. So partial n partial x equals partial m partial y. And we can go ahead and solve this as an exact equation. Solution would look something like this. We can start by taking this term here, integrating with respect to x. That becomes just y over x plus possibly some constant in terms of y. And now we double check that. Partial f partial y according to the fact that this is f of xy would be 1 over x plus the derivative of g of y. And now if we go back, we see that partial f partial y is 1 over y plus 1 over x. So that means that g prime of y has to equal 1 over y. So then what would g of y be? G of y should just be natural log y. So we're done. f of xy, and here, so I don't make that same mistake again. F of xy is right here. It's y over x plus whatever I got for g of y, which is right here, natural log y. So the solution is y over x plus natural log y equals c. Okay. Sorry we kind of rushed through there at the end. I know you guys got to go. Drive safe. And